Hello everyone. Thank you very much for giving me an opportunity to present my research work in the national webinar competition. Today I am going to talk about EEG-based investigation of the fundamental frequency difference coding for source segregation in elderly normal hearing adults. This work is currently being supported by ANRF under SERB CRG scheme. Let's assume that we are in a noisy environment. Have you ever wondered how we are able to comprehend and understand the fellow colleague or friend in the presence of multiple speakers? This may look very trivial. Our auditory system have a remarkable ability to segregate and understand a target person's speech in the presence of multiple speakers. One of the most dominant segregation cue is the difference in the fundamental frequency between the speaker. In the same scenario, if I bring in the older adult with normal hearing, they may face a lot of difficulty in segregating and concentrating on a target person's voice. This is exactly what we want to investigate in this particular project. In a multiple speaker scenario, we rely on F0 difference between the speakers. F0 different utilization is dependent on how well listeners discriminate fundamental frequency. Thus, our goal is to understand the neural representation underlining the F0 discrimination in younger and older adults with normal hearing. The neural responses of the brain were obtained using the EEG signal, which can be directly applied to human subjects. Our stimuli consist of two tones. One is the standard tone, which is always having a fundamental frequency of 100 Hz. Another one is a deviant tone, where the fundamental frequency is varied from 103 to 179 Hz. The tone duration for both the standard and the deviant was set to 400 milliseconds, just to make sure that we have a sufficient F0 based segregation ability Q available. Tone level were presented at 65 and 75 dB SPL. 65 is a normal conversational speech level and 75 is a slightly louder than the normal. So our subject here, a series of standard tone, and all of the sudden the deviant tone is presented. Our subjects were instructed to click the mouse whenever they hear a deviant tone, and the presentation of the deviant tones were randomized. We recorded EEG responses from 8 different channels, 3 at the frontal, 2 at the central, and 3 at the parietal. So this is the EEG cap as shown here. This is the EEG cap, and then this is the ring electrode, and then this is the connector, and then it is connected to the live amp. Subject wears this EEG cap, and then we present our stimulus through the insert earphones, and we get the EEG responses. Later on, we computed the event related potential for standard as well as the deviant tone, and we analyze P300 component, which is a measure of F0 discrimination in active listening mode. Figure here shows the grand average ERP responses from 20 younger adults with normal hearing. So the first column here is the standard, the second column here is the deviant tone. X-axis is in time in milliseconds, Y-axis is the voltage in microvolts. Different color here represents the electrode responses. Clearly, for 3 Hz F0 difference, there is not much of the difference between the deviant trial with respect to the standard trial. As we increase the F0 differences to 26 Hz, we can see that the P300 component slightly starts to emerge from the parietal region. With further increase in the F0 difference to 79 Hz, we can see a dominant P300 component, which is emerging in both at P3, P4 and PZ. So all of the 3 parietal regions. To further analyze it, we actually computed the scalp map, which is nothing but the mean average of the amplitude between the specific time window. In this case, we selected between 320 to 350, where we can see the complete peak which is going up and down. So here we can see that for 3 Hz, the scalp map between the standard and the deviant is pretty much the same. blue indicates the low color. As we increase the F0 differences, we can see that there is a higher parietal responses in the case of 79 hertz for the deviant tone. Okay. Now, for 26 hertz, we saw a very low responses of the parietal. So we were curious to know why we were getting a lower response. Is there a way, if we increase the sound level, the responses at the parietal can be improved? So to further investigate that, what we did is that we increased the sound level and we did the similar study. This is the plot scalp map for 65 dB SPL and this is for the 75 dB SPL. As can be seen clearly, P300 amplitude benefited due to increase in level for the 26 Hz F0 difference. Later on, we did exactly the same study for 10 older adults with normal hearing. Currently, the data collection is in progress. So, in the standard trial, the prominent difference with respect to the younger normal hearing subject, which we saw, is that there is a slight higher responses of the standard trial, indicating that the older adult might have a attention switching issue going from a standard versus the deviant and back and forth. As seen in the younger normal hearing subject data, we can see that the P300 amplitude or the component being seen for 26 Hz and 79 Hz. But these values were relatively lower as compared to younger normal hearing subjects. Again, we did the scalp map 65 versus 75. Here we observed that for older adult, we can get a stronger P300 component with a further increase in the sound level from 65 to 75 for 79 Hz F0 differences. And if we see a little bit more closer, 26 Hz F0 difference is also benefited with increase in the sound level, but it is less significant as compared to the 79 Hz F0 difference. Our preliminary results from older normal hearing subjects reveal that P300 amplitude is reduced with increasing age. Consistent with younger normal hearing subjects, P300 amplitude improved with increasing F0 differences as well as the tone level. A reduced P300 amplitude may contribute to impaired processing of F0 differences, thereby leading to a lower identification scores in older adults. These are my group members who have been constantly working on this project, and I would like to thank all my subjects who have actively participated in this study. Thank you very much. Namaste.